So, Madam President of the Crafoord Foundation, and Mr. Fisher as well, members of the Crafoord family, as you all can imagine, this is an extraordinary time for me. I've never had an experience anything like this, and it's been fantastic the last few days, but I'm going to stop there because it's going to continue to be fantastic for me, I know, for the rest of the evening. And I was asked to give an autobiographical talk. So I'm going to talk about building of high mountains, but not at any length. Then I'm going to move towards why we have had ice ages over the past 3 million years. But to get there, I'm going to go via tropical islands. This is work that starts with what I've been doing all of my life to what is literally what excites me today and what I'm pursuing, and in fact, some of what I will show you is new. I could have sworn I pushed that button. Oh, maybe I have to do it with this. I did that one. We had some problems earlier, I wonder.
Let me take you out and then start again.
Well, okay, while Gia does that, I'm going to ask 3 questions. One, the simple one, how do we make mountain ranges? Then I'm going to ask a question about how do climate and mountains interact with one another? And then I'm going to go from that, yes, there we go. What geodynamic processes build mountain ranges and high plateaus? How do climate and mountain ranges interact on geologic timescales? We're not talking of modern timescales. And then what geologic processes and what growth of which mountains made recurring ice ages possible? So I'm going to show you this movie one more time, actually 3 more times. This movie is made by Tanya Atwater, who is present today. And I'm just going to run this through for you once. See if it works this way. There. Oh, sorry, didn't mean to stop it. Just watch it go. This is a faster version than what Gia showed you. And then after it's done, let's do it again. But this time, let's focus on the edge of India. Here we have the Indian subcontinent, the Eurasian or Asian continent to the north, a chain of volcanoes along the southern edge of Asia, an ocean in between, and the Indian plate with oceanic lithosphere plunges beneath southern Asia. Now, the Himalaya will be built entirely by rock on the northern edge of India. So let's watch that, focus on that part of this. Focus on this. First, India dives underneath, a new fault forms, you build mountains, a new fault forms, and you build higher mountains. All of that rock was part of India, not part of Asia. And that's where the high peaks are. Mount Everest might be that peak right there. And if we make a cross-section through southwest on the left, Indian crust, diving underneath the Himalaya, the ancient edge of Tibet, of Asia over here. So this is southern Asia. All of the Himalaya across here is actually Indian crust. And I should say this was recognized 100 years ago by Augusto Ganser, a great Himalayan geologist, a Swiss scientist who worked in the Himalaya in the 30s, and he figured this out. This isn't new. There's detail that is new, of course. The Himalaya consists of slices of the Indian crust. All of this is Indian crust thrust up over on top of a piece of crust, it thrust on top of another, this on top, and out onto a basin out in front. So the Himalaya, it consists of India, but India that's been attached to the southern edge of the ancient Asia. If we look at this, step back and look at it in another way, this is a simpler cross-section where we have crust and the uppermost mantle. This is a strong part of the Earth, the lithosphere, and we can think of this as an elastic plate that bends down. It's loaded by the weight of the mountains, and it's flexed down at the northern edge. And because it's flexed down, there's a basin that forms that's filled with sediments in here. This is called the Ganga Basin. Ganga, the same as the Ganges River in India. It just fills up with sediments in here. And if we look at a map across this region, the Tibetan Plateau, this area, the Himalaya following down along in here, this of course is the Indian subcontinent. There's a basin down here where the land is very flat. The Ganges River or Ganga River flows down in here and empties into the Bay of Bengal. This is a basin full of sediment. And just as a thought experiment, I would like to leave you with a question. Is Mount Everest, does it stand higher than Mont Blanc in the Alps simply because the Indian plate is stiffer than the Eurasian plate, the European plate that plunges under the Alps? The European plate bends much more, so it can't support the same height of the mountains that we have in the Himalaya. Now I want to show this film again, this animation, Tanya's animation. I should say this was given to me on my 60th birthday. It honors all of my prejudices, but not necessarily all of the facts. It was made for me, so I get to show it. This time I want you to watch Tibet. The Tibetan Plateau is going to grow in this area. You might also watch the Tian Shan, another mountain range that will grow here. Though I'm showing you this, but I'm then going to talk about the Tian Shan because we think they both have grown by the same process. Oops, sorry, didn't mean to do that. Let me start this again. So India comes and collides. Now watch, there are many faults across Tibet, and the whole of the crust of the Tibetan Plateau becomes thicker. The same is true out here in the Tian Shan. So a wide zone of deformation with many faults, not just a fault along the edge to make the Himalaya. A broad zone is forming in here. Now, as I said, we think the Tibetan Plateau has been built by the same processes that are happening today within the Tian Shan. And so the Tian Shan is an easier place to study, to watch this happen. Tibet has evolved, it's at a later stage. So I'm going to turn and consider the Tian Shan up in here. And so just blowing that part of the map up, this is the Tian Shan. Dimensions, this is approximately 300 kilometers across. And what you see, the green shows high terrain, high mountain ranges. The white is even higher. The highest, the only peaks in the world above 7,000 meters and not within the Himalayan chain are in this area of the Tian Shan. This is a high mountain range. But within it are basins. These are basins in here. Isikul, a lake, sits in a big basin in here. The Turfan Depression up here is in fact below sea level. It's the lowest place on Earth after the Dead Sea in the Middle East. And it is here because there are faults that dip under the range to the north and dip southward, and these have loaded the crust and pushed it down, and the erosion rates are not high enough to fill this with sediment. The floor of Isikul is not deep, but the floor beneath the sediment is way below sea level, much below sea level. So I'm going to focus in on just one segment in here and show you a part of this area that we studied many years ago. So this is Isikul again. We're looking at one of these basins. This is a photograph looking to the east, south on the right, north. You see across here a high surface, and then it drops down, and another surface going across here. That surface was the same surface. It was a terrace, or it was the floodplain of a river at some time in the past. You see the same here, a surface coming across, and then it steps down here to a lower level in here. Don't be deceived, that's a road. That's not a geologic feature, and that's our camp over here where we lived when we worked in this area. Then down lower, another terrace here coming across steps down to a lower level. And then down near the bottom of the river, a still smaller one. And then you have the river down at the bottom, wandering, meandering back and forth. Now we make profiles across these regions, this region, that one, and those. And they're shown here. The bottom one, there's just a small step in the topography, just a couple of meters. The next one, this one, there's a step of 5.5 meters. The next one, 12 meters, and what's happened here is very simple. The part on the north side has been thrust northward over the region to the south. The different sizes of displacements are there because this is an older terrace. The river once flowed up here, then it incised down to this level, flowed along and made a floodplain here, incised again down to that level, flowed along here, and now in the future the river will probably cut deeper yet again, and this fault will then offset the old river terrace. The important point here is that this is within the mountain range. This is not like the Himalaya. You have basins with mountain ranges thrust on top of the basins. In this case, the faults dip to the north. In this region over here, another fault dips to the north, over here to the south, up here to the south, different directions, many faults in the middle, not just one fault. if we do a cross-section across the northern edge of the Tian Shan, this is Kanatbek Abdrakhmatov, a Kyrgyz geologist who worked in this area. So the northern edge of the Tian Shan, one thrust fault here. The rock has been thrust to top, the rock to the north, and then flattens. Another one here, another thrust fault, and then there'd be a series of these to the south. So this is a very different style. It's not this style, where you have one active fault at any given time. You're underthrusting the entire Indian crust beneath one fault and then another fault and stepping. In the Tian Shan, you have many faults active at the same time. A fault across the northern edge, a fault within here, another one within here, another one within here, another there, and then again across the southern edge. And we think this is the way crust has thickened within the Tibetan plateau as well. So rather, we have many steeper thrust faults than in the Himalaya. They slice through the range and create ranges, the high terrain in here, separated by intermontane basins, the lower areas in here, including Issyk-Kul and the Turfan Depression, which is below sea level. Now, if we look at what the amount of time it takes, Tibet in the Himalayas seem to have required 50 million years to be built. For those of you who aren't geologists, this of course seems like a long time, but the Earth is 5 billion years old, so 100 times that. This is still a long time. The Tian Shan, there was a mountain range 25 million years ago. Probably most of it was built in the last 10 million years. But again, we're talking long time. The Alps required tens of million years to be built. Well, 25 years ago, as I was working on mountain ranges, I compiled something that looks like this. You can't digest this, but if you give me a mountain range in the world, someplace in the Rockies, the Andes, the Alps, any place, Scandinavia, mountain ranges, I will find you a good geologist, and many of these, Augusto Gonser, the expert on the Himalaya, where is he? There he is. I'll find you a good geologist who will claim that the mountain range rose recently in geologic time. And if we take Fennoscandia, you can all pronounce this better than I can, but Hjellstuen, in 1999, his colleagues said since 2.6 million years ago, major apyrogenic uplift. Apyrogenic means the whole region went up together. And wherever you go, in Spain, or in France, I should say, the American Massif Quaternary uplift. De Sitter, world expert, he's no longer with us, on the Pyrenees, Pliocene uplift. Trumpi, the world expert on the Alps, Pleistocene uplift. Pleistocene would be the last 2 million years. Wherever you go in the world, I'll find you somebody who said the mountain range went up. And I contend we don't have a process that can do this, so this is a deception of some kind. So I'm going to switch topics now, and how do climate and mountain ranges interact on geologic timescales? Now, at the time that I was thinking about this, a very influential paper was written by Maureen Ramo, Bill Rudiman, and Philip Froelich. It was followed by a more influential paper by Maureen Ramo and Bill Rudiman. But in this first paper, they said, we propose that increasing rates of uplift and erosion of the Himalayas, the Andes, Tibetan Plateau have contributed to a significant increase in the global rate of chemical weathering since the late Miocene, since approximately 5 million years ago. Chemical weathering, this is the dissolution of rock, acids in the water, carbonic acid has CO2 in it, dissolved the rock, and this for them was a very important process. This is excellent work, I should say. I'm going to criticize it, but it's excellent work. So we usually attribute this to Maureen Ramo. She was a student at the time, and what she said was you have an accelerating rise of mountain ranges, increased chemical weathering of rock, as I said. Now the key to this is that when you weather the rock, you extract carbon dioxide, CO2, you withdraw that from the atmosphere. And this then will cool the Earth, just as carbon dioxide added to the atmosphere today gives us global warming. Taking carbon dioxide would cool the Earth, and you get ice ages. This was her idea. This collection, these 5 parts, were hers. In fact, this rests on a very solid foundation, going back to 1896. Svante Arrhenius, you should all know his name. This was a giant. He realized that CO2, if CO2 were withdrawn from the atmosphere, the Earth should cool and you should have ice ages. When he wrote this paper in 1896, I recommend all geologists read this. This is just a landmark study. He was attacking the question of why did we have ice ages? And this was his suggestion. Maureen Rameau's contribution to this was to say, well, maybe the mountain ranges eroded and weathering took place. Well, let's just first talk about ice ages. Another animation by Tanya Atwater. I'm going to show you this twice. This is centered on North America, but you see Fennoscandia. Let's just focus on North America. Oh, I didn't mean to do that. I meant to do this. So at some point, ice forms over Canada, spreads southward across the United States, spreads southward across Fennoscandia into Northern Europe, lingers around here for a while, and then it retreats, and it retreats quite quickly, remaining in Greenland. This is centered on North America because she knows North America better than she knows Scandinavia. But she's here. She's probably shy. I won't point her out to you. But if any of you know and can help her, she's very eager to know more about that region. So please talk to her after today. Okay, I'm going to show this one more time. Just watch Fennoscandia. You form ice in the northern part of Sweden and Norway. It spreads out over Germany, down onto the Faroes Islands, not quite Europe. The coastlines have changed because sea level has dropped and you retreat it back very quickly. There's Britain, Iceland, and up in this area. Okay, the best measure that we have of temperature, or crude measure of temperature, but the best long time series we have relies on oxygen-18 isotopes. Most water consists of 2 hydrogen and 1 oxygen-16. Oxygen-18 is rare. It's only a few parts per million in general. But this is thought to depend on temperature. And these are recorded in planktonic foraminifera, microorganisms that live in the ocean and sink to the bottom. And this is a well-known compilation by Jim Zakos and his colleagues. And what you see is this varies all through this last 5 million years. The present is here, 1, 2, 3, 4, 5 million years ago. A drop that the present day we're way up here, but 20,000 years ago we were down here with the last ice age, and we've oscillated over the past couple of million years. We've had big ice ages since about 1 million years ago, but the first ice age actually was here at 2.7 million years ago. Now, one way to look at this is as a series of ice ages, but another is just to look at the long term. And one of the giants of modern physical oceanography, particularly tropical oceanography, George Philander, he likes to say ice is really incidental to the ice ages. My glaciologist friends are very offended by this statement, of course. But the logic is simple. If you smooth through all this, average all this smoothing with a window, 200,000 year window, you get this red curve, a steady decrease. And the point is that this suggests over the past 4 to 5 million years, there's been a steady decrease in temperature in the high latitudes. Crudely, this would go from of order 1 degree Celsius to, at the time of the ice ages, below, so of the order of 7 degrees Celsius, negative 7 degrees Celsius. But this long cooling process. And so the rest of this talk is really going to focus on why did that happen. But first I've got to bring you back to the mountain ranges. So if we try to be quantitative, estimates of uplift, and you'll understand the quotes in a second, uplift histories of some high mountain ranges and plateaus. Let's start with Tibet in the Himalaya. Here we have estimates of elevation 1,000, 2, 3, 4, 5,000 meters, going back 10, 20, 30, 40, 50, 60 million years. Shuren is a Chinese, I think he's no longer with us, paleobotanist. So what he studied were fossil plants in the rock. And if we take it as example, roughly 5 million years ago, he found at elevations nearly 5,000 meters high, he found fossil evidence of plants that today live only at 2,500 meters. So he inferred that these plants cannot live today at 5,000 meters. He inferred that the plateau had risen by 2,500 meters. Of course, this ignores cooling of the Earth. If we remember that we've cooled the Earth over the past 5 million years, I would contend that these plants that today cannot grow at 5,000 meters could have grown at that elevation 5 million years ago because the planet was warmer. If we look at these others from the Pakistan Himalaya, Nanga Parbat, or from the Bolivian Andes, the Cordillera Oriental, these are estimates of rates. They're given as rates of uplift in millimeters per year, 1, 2, 3, 4, 5 millimeters per year, going back to 4, 6, 8, 10 million years ago, or lower rates in the Andes up to 1 millimeter a year and going back over longer periods of time. But in fact, these are not rates of uplift, these are rates of erosion, or more precisely, they're rates that rock cooled because of erosion. So these are not, although they call them uplift, this is not uplift of the surface of the Earth. This is erosion of the rock off the top. And this ignores glaciation. In the last few million years, we've had a big increase in glaciation. Glaciers tend to erode more rapidly than rivers. And so we would argue that this is not indication of uplift of mountains, but again, it's a consequence of climate change. So 25 years ago, Philip England and I wrote a paper, which we were very clever with our title, although we misled people, Late Cenozoic of Uplifted Mountain Ranges and Global Climate Change, Chicken or Egg, which comes first? And we argued the temporal correlation of late Cenozoic glaciation with phenomena commonly attributed to recent uplift is inescapable. Can't deny that. But assigning the ultimate cause of the climate change to the late Cenozoic uplift, that we reject. Instead, we see the phenomena commonly used to infer recent uplift are actually a consequence of climate change. So we would invert the logic on this. And a way of looking at this is people focused on uplift of mountains all around the world, the whole globe. As I said, I can find you a mountain range, I can find you a geologist for every mountain range, find somebody who said it rose recently. But you need a global process to make all the mountain ranges go up around the world. They should have focused, or it would have been better to focus on the simultaneous increase in the dissection, erosion, and wearing down of mountains. Because global climate, there's a global process that can create the same observations that we're seeing, but have nothing to do with changes in elevation. Okay, now I'm going to move to the subject that, one of the subjects that motivates me, has motivated me for the last 20 years, and in particular right now. What geologic processes made recurring ice ages possible? This is a complicated story. This is the hardest part of this talk. So I'll give you an outline and then I'll take you through pieces, and maybe you won't remember all the logic until the end. But a key is the growth of islands and mountains in Indonesia. You don't think of Indonesia as even mountainous. We call Indonesia the Maritime continent because it's lots of islands in the sea, in the maritime environment. This, we say, enhanced rainfall in this region, and that transformed a state that did, 5 million years ago, resemble El Nino, the situation we have rarely in present-day climate, to another more like our present-day La Nina climate, as we have today. And that transformation from El Nino to La Nina denied Canada long summers that melted winter snow, so we could make ice ages. And then with shorter summers, ice could accumulate, and we could have ice ages with that. So first, this is a map of Indonesia. Here's the northern coast of Australia, the island of New Guinea, and here, Halmahera, Sulawesi, Borneo, part of the Philippines. And many of these islands have emerged recently. Timor, for instance, this island right in here, 2.2 million years ago lay 1,500 meters below sea level. Sumba has emerged 4,000 meters since 6 million years ago. Halmahera, big island, most of this has emerged in the last 5 million years, and other small islands, Buru and so forth. The mountains in New Guinea are quite young, of order 5 million years, and most of New Guinea was below sea level 5 million years ago. So this is going to be part of the story that I'm going to give you. Oh yeah, that's right. This is now a comparison of what the normal state today, we call it La Nina, but La Nina is a slightly enhanced normal state versus El Nino. During El Nino, one has a warm western tropical Pacific. So Australia lies here, in North America, Florida. South America lies here. So this is the equatorial Pacific. The western Pacific is warm. The warm colors suggest warm surface water. There's ascent, warm water, warm air rises, ascends to the top of the troposphere. moves eastward, descends over the eastern Pacific, and then the winds blow back along the equator. That westward wind then pushes the warm water up against the Indonesian region. During an El Nino event, what happens is this ascent over this part, over the maritime continent, weakens, and the locus of warm water moves eastward. So the whole of the eastern Pacific becomes warm, and then the warm water in the eastern tropical Pacific affects the atmosphere, which then sends, through atmospheric teleconnections, signals to other parts of the world. So this is a map of El Nino teleconnections associated with warm episodes, El Nino events. Indonesia becomes dry and hot because it has fewer clouds. The eastern Pacific becomes warm and wet, and important for this is Canada becomes warm. During El Nino, ice on the Great Lakes is much thinner in the winter, and Canada is a warmer place. And the argument I'm giving you is that back a long time ago when this was warm, Canada should have been warm as well because of this atmospheric teleconnection. Now, to look at this again, in a similar way, this is real data. Australia lies here, Mexico, South America, the Pacific. This is the normal situation, a warm western Pacific out in here and what's called a cold tongue reaching out into this area. But during an El Nino, the whole of the Pacific becomes warm. The whole of the equatorial Pacific becomes warm. Now, what we can do with not I, but what others can do with a big ship drilling a hole into the bottom of the ocean, getting sediments, and what Kira Lawrence, Jungwei Liu, and Tim Herbert have done is take sediment going back the last 5 million years, 1, 2, 3, 4, 5 million years, estimate the sea surface temperature, that's the red line in here, and what you see is a cooling over this period, approximately 1 degree Celsius per million years, cooling along this period. So back 4 million years ago, the sea surface temperature was about 4 degrees C warmer than it is today. And this is these are inferences drawn from marine fossil record in the Pacific by these authors. In a synthesis of more recent data, Petra Deakins, Christina Ravello, and Michael McCarthy put together a summary, and the background is an El Nino-like temperature distribution, and maybe it's hard to see, but the eastern Pacific at several sites is shown to have been warmer back 4 million years ago than today, and other sites even much warmer. I'm not going to talk about that, but this is pertinent. The Western Pacific, a negligible change in temperature. So how do we move from warm Eastern Pacific to Canada? I'm going to show you some work by Peter Hybers, and the concept that we use is called positive degree days. If you have a temperature, a mean daily temperature that's positive, warmer than freezing, we keep it. So imagine we sum for over a year. The first day, I equals 1 is January 1st. I equals 365 is December 31st. We take the first day. If the temperature is positive, we multiply it by 1. We keep it. If it's negative, we multiply it by 0. We throw it away. And then we move on through the year, adding up the total number of positive degree days. If the mean the mean daily temperature were 10 degrees Celsius every day, we would have 3,650 positive degree days. And here's a map showing the mean values that you get. Each of these dots is a meteorological station. Here's Greenland, Scandinavia, Siberia, northern Canada. So the rim around here is about 40 degrees north, and obviously you have more positive degree days at lower latitudes than you do at high latitudes, with a scale going from 1,000 to 4,000 positive degree days. Now, what happens during El Nino? Because this is what we care about. This is what I just showed you. This is now for El Ninos. And what you see is Canada has more positive degree days. These are anomalies, differences between what's measured during an El Nino and what the average conditions are. Here's a scale, it's small compared to that, 200 positive degree days, but that's actually quite a few. You get more in Canada when you have an El Nino event. So what Canada does gives you more positive degree days. Glaciologists talk about melting of ice that's associated with positive degree days. And the thought is that 200 positive degree days is enough to melt much of the summer snow. Well, if we take a scaling relationship between the El Nino, the Eastern Pacific sea surface temperature, and positive degree days, we can use that and apply it to the past. So this plot here is temperature in the Eastern Pacific that Kira Lawrence and her colleagues had obtained, going from the present, now this is a confusing scale, 1,000 kiloyears, so this is 1,000,000 years, so present 1,000,000 years, 2, 3, 4, 5 million years ago. Kira Lawrence's sea surface temperature is quite jagged. Peter Hybers then just fit a simple red curve through the middle of this as an average, because we think much of this scatter is noise. And then if you take the scaling relationship, you can predict how many positive degree days you would have had in the past by scaling it to this red line. This red line, this mean temperature going back where it's 4 degrees C warmer 4 million years ago than it is today, your positive degree days would have been more by several hundred positive degree days. And he puts this blue line through the bottom when the first ice age began right here. So the logic would be, before this time, you could not have ice ages because Canada was too warm. Since that time, you could have ice ages. And in fact, over the last 1,000,000 years, most of the time, you would have had an ice age, as we observe. Most of the last 100,000 years, you would have been under a lot of ice right here. You would have been 2 kilometers below the ice above. So most of the time, there has been ice in this area. Okay, this is taking that. Now, switching back to the present, this is a map of the Indonesian area, so the island of Sumatra, the island of Borneo, the Philippines up in here, Sulawesi, New Guinea, Java is in here. This is the northern edge of Australia. And this is a map of rainfall. Today, modern day rainfall rate measured in millimeters per day. And the red areas are more than 12 millimeters per day. And if you look at the map, what you see is the red areas where the heavy rain occurs is either on the islands or near the islands. New Britain in here, New Guinea in this area, Sulawesi, Borneo, Java, Sumatra, off the coast of Sumatra. The islands are acting as attractors for rainfall. And there are many islands in this part of the world. And just as an image, this is a photograph taken by an eminent physical oceanographer, Arnold Gordon, looking across to Sulawesi. So there's an island under there, and you have this huge cloud. That's 14 kilometers high up here at the top of the troposphere, just this enormous cloud. Islands are an attractor for rainfall. Now I'm going to show you now another animation. This is now numerical calculations carried out by Tim Cronin. He was a student. He just defended his PhD thesis in February at MIT. And this takes a bit of time to explain and a little bit of time to run. But this is a grid that's 380 kilometers on that axis, 380 kilometers across. So this is a region 380 by 380 kilometers. In the middle, in that black circle, there's an island. This is a numerical calculation, so of course all this is simulated. The colors are showing you sea surface temperature, alas, in kelvins, not in degrees Celsius. So the temperature there would be, the red would be 21 degrees Celsius. Down here, the temperature would be about 9 degrees Celsius in this area. And I'm going to run this. What you see with the white are clouds that are forming and rain that's falling. Under the clouds, it's blue. It's cold. It's cold because the rainfall drags the cold air down with it, so you have rapid descent. Now, we started this at midnight local time. The island is getting cooler. It's cooling because it's radiating out into space. The rainfall around the island in the ocean just goes, it doesn't see the diurnal cycle. Now, very soon this becomes hot. Morning, now you've crossed midday, you're now 2 in the afternoon, it's becoming very hot over the island. You draw moisture in and suddenly you get big rainstorms with rapid descent, cooling the island, a flow, an outward flow, and you're back, and now we're almost at midnight again. I'm going to run one more day. So it's cooling during the night. You watch it get colder because the land surface is radiating into space. It cools, and it keeps cooling until about 10 o'clock in the morning. So we're now 8. It's getting colder. 10, and now it gets hot again. The surface warms up because it has a lower heat capacity. draw the moisture in, big rainstorms, and then the descent, the downwelling flow associated with the rainstorms cools the surface, and you spread out and cover the area. Now what Tim has done, Tim Cronin, what he's done is he's run several experiments using this code, and what's plotted here is the mean temperature, the surface temperature in blue, and the mean temperature in the atmosphere here in degrees Celsius as a function of the fraction of area that's island. So this would be 10% island, this would be 20% island. And as you increase the area covered by islands, you increase the temperature in the atmosphere above. You increase the temperature, what that will do is create a pressure gradient, and that pressure gradient will drive a flow. So we're going to go back to the circulation, the same plot from Mark Kane that I showed you earlier, with a simple, much simpler view over here. And if you have ascent over the Maritime continent, ascent, you go to the surface, as you would have over Indonesia. That, from Tim's calculations, would suggest you have a warmer troposphere. That'll create a higher pressure aloft. The air here is warmer here than it is in other places. So that pressure gradient will drive a circulation of flow of the air aloft, eastward and westward as well, along the equator, eastward along the equator from the Maritime continent out over the central or eastern Pacific. Eastward flow aloft, as I just said. Then you have descent over the central and eastern Pacific, descent in this region or over in here. And then the return flow, westward flow near the surface, and that maintains the warm pool in the west. So this westward flow in here maintains that warm area out in here. Today, this is the situation we have today. So more rain, what we're arguing though, is more rain over the islands creates a La Nina-like state. It creates this situation. Less rain over the islands, you move towards an El Nino state, more like this. Well, more islands, therefore, would mean more rain. More of a La Nina-like state. Fewer islands would mean less rain. More of an El Nino-like state. If you had fewer islands over the Maritime continent, you would have a state more like what you have during El Nino. And more islands, more rain, La Nina, then you have the potential for ice ages because of the teleconnection to Canada. Fewer islands, less rain, El Nino-like conditions, you won't have ice ages. And we're arguing this was the state until just a few million years ago. Well, what's happened in Indonesia over the past 5 million years? This is a map, Sumatra, Borneo, Java, Sulawesi, Mindanao, New Guinea, Australia. If we look back 5 million years ago, much of this area was submerged. Much of New Guinea was underwater. The red shows areas that were submerged 5 million years ago. Most of Halmahera, that island there, was submerged. And I moved these back to where they lay 5 million years ago. Timor was underwater. Sumba was underwater. A quarter of Java was underwater. A quarter of Sumatra was underwater. So today, in this region, the land fraction is about 18%, but 5 million years ago, it was 10 or 11%. So we've gone from a state with few islands to many islands. And then, just to take you through this logic, more rain falls on and near islands than over open ocean. More rain over islands means a stronger Walker circulation, stronger easterly winds in the Pacific, a La Nina-like state. A stronger Walker circulation means a cooler eastern tropical Pacific, which is not El Nino. So we do what geologists do all the time. We substitute space for time. So more islands means more rain, stronger Walker circulation, stronger easterlies, and a cooler eastern tropical Pacific, and this is what allows ice ages to begin. Now I should tell you, this is very speculative, and I could be completely wrong in what I've told you, but this is why science is fun. You stick your neck out and you pull it back quickly when the guillotine comes, but you still, it's fun to have it out there. So just to summarize, I've tried to show you something about slow growth of mountain ranges and high plateaus and how that happens. Switched to the arguing that rain over tropical islands and over an increasing number of islands will affect our climate, rainfall over islands, and by increasing the number of islands, we could develop ice ages this isn't an ice age. This is in Tibet, looking across an ice sheet, a big ice field. But this is the best I can do for a photograph of an ice sheet, at least that I've taken. So I would like to end again. Thank you to the Crafoord Foundation for extraordinary generosity and for a phenomenal last few days that I've had here. Thank you.
Thank you for that spectacular talk. We'll take a couple questions before we move into a break. So, does anyone have a question? We have Anders.
Thank you very much, Peter. Very interesting talk. Now, I wonder here, I suppose what you're saying here is that the convective cells are greatly affected by the distribution of landmass.
Yes.
Yeah. So, have you made any tests as for ancient supercontinents and different locations of continental mass? How would that affect climate? Or can you see any correlation with, for instance, the Rodinia and the snowball Earth?
I think the answer to all of those questions is no. I haven't done that. I haven't thought that far back in time. Rodinia is too old for me still. I contend I'm still a young man, despite what I might look like, and that's way back. So I haven't thought about that, and I'm nervous about risking what I might think if I did think, at least in public. So I'm sorry, I'm not going to give a good answer.
I suppose what you're predicting is that we should see some sort of correlation if you're right.
For sure. I mean, I have an old colleague who's studied paleoclimate his whole life. He's a 90-year-old man, and he would argue that all of climate depends on tectonics, depends on where continents lay, where the gaps in the continents, where the gateways in the oceans lay at different times in the past. All of that, all of past climate will depend on that very strongly. So I don't have any doubt about that. What I don't want to do is make a prediction. I don't know enough to make a prediction.
Thank you.
More questions? Yes, we take one in the back.
Yeah, it was a very interesting talk. It was exciting. I was very thrilled, especially to see the last part about the ice ages and the Indonesian islands. I was just wondering if has that been published, or is it something you're doing right now? Or because it's, for me at least, it will be quite important because from perspective of biodiversity, and especially from the diversification of birds, it would be quite important to have some of these detailed data on when the Indonesian island emerged.
Okay, you asked several questions. There is a little bit of it published. I showed you a picture with Catherine Daham's work in 2007 about rainfall, and so the basic idea was published then. I worked with her. She was a student in Colorado. The Tim Cronin's work is not published yet. It's with some hesitance, but he's a great guy, so I nearly dropped that. That's not yet published. So the atmospheric sciences, that will be submitted to the Journal of Atmospheric Sciences, perhaps today, I don't know, but very soon that will be submitted. The islands, the maps of when the islands rose, that's not published. That's my task for the summer, what I want to write up. But it's based, of course, on work of others and an enormous amount of work of others. So I would be, in fact, I should back up. If you want a shortcut to this, it's based in large part by work by Robert Hall, geologist in Britain, who's made animations of the history of this part of the world, and he's published a lot. So maybe not half, but a large fraction of this map comes from his work. And I could give you 100 references. I think it will take 100 references to cover all of this.
Okay, we'll take one more question before the break.
Do I press? No. Sorry. I'm just thinking about these, I don't know, these percentages you have up here. Are these from a global scale, or how much would that increase in land mass being on a global scale?
Oh, tiny. It's the good question. It's basically this region included in this box in here. So part of it is because 5 million years ago, Australia lay farther south. This is 14 south. You can see Australia's moved in. So it's just in this maritime continent region and near the equator, within 10 to 12 degrees of the equator. No, this is a tiny fraction on a global scale, but it's nearly a factor of 2 in Indonesia. And if you believe everything else I told you, and if you believe everything else I told you, I have a bridge you might want to buy that connects 2 boroughs in New York City. Maybe you don't know that joke, but the Brooklyn Bridge has often been sold for a bargain. No, there's a lot of speculation, of course, in here. But this is a big change in the fraction of islands in this area, and the islands are crucial. And I left out a key step, and that is because it's just too much to cover. In fact, I talked too long. If you correlate the winds in the Walker circulation with rainfall over Indonesia, the correlation is huge. When it rains in Indonesia, you get a strong Walker circulation. So there's really a link between the rain and the Walker circulation. And now there's a correlation of the rain to the amount of islands. So I'm not sure I want to sell the bridge quite yet.
Great. Thank you.
Thank you.